But it behooves us to do the same kind of thing we did with the numerical integration, which is say, well, how good is this? Fortunately, in this particular scenario, this is a differential equation that we can solve by hand. So again, we can compare against the exact answer. So we actually have a formula for what happens to objects that cool down in this particular environment. And you notice there's a -5 and an exponential decay. So we're going to plot that as well. So we're going to add the analytic prediction, which is t is equal to lin space. Let's call it t2. Line space. Lin space. Lin space from 0 to t end. And y2 is 25 times an exponential of it's actually minus k times t minus 5. Hold on and plot t2 and y2 in red just for fun. Nope, didn't like that. Oh, right, t2. T2. There we go. Okay. So what do we see here? We see that they're close. Like we're not talking crazy talk here with Euler's method, but there's a note, like a visible difference. This is not a super accurate method. If we zoom in here, there is a very visually apparent difference between these two values. And whether I care about a 0.5 difference in temperature depends on the context, but the question would be, can we do a bit better than that in principle? Okay? So it's okay. Roughly speaking, it's doing the right kind of job, but it's not very accurate. So notice at the beginning, we can actually see some stuff here. Sorry. There we go. So at the beginning, things are perfectly matched. We can actually see how Euler's method works. Euler's method was following straight lines. So you can see that blue line. Let's see if I can zoom in right on that first interval. There we go. Both things have exactly the same slope at the beginning. Why? Because one's the analytic solution that exactly satisfies dy dt equals. And our other one, we knew exactly where we were. So we had exactly the same value for dy dt. We had exactly the same value for the slope. The difference is the blue line was just then followed that one slope religiously for the full time interval down to here. Meanwhile, the red line, well, as the temperature difference shrank, the slope got less steep because there's less temperature difference, so it cools less quickly. And so it peels off and goes a little bit above. One's the straight line approximation. One's the, if things could be fed back and changed as we went, it would give us the red line, which curves a bit more. So it's a subtle difference, but it's there. We also see some variation at the very end of this, which isn't too surprising. Not as visible on the first zoom in, but the final prediction of where we end up is going to be a bit different between these two solutions. We're actually going to focus on that next. Because sometimes, in many contexts actually, it's where we end up at the end of the simulation that's the most important arbiter of error. And so we're going to use that here for our analysis as well. So what we're going to do is print out the error at the end of the simulation and see what happens as we change the number of intervals. So we'll have our plot here, get the error at the end of the simulation. Where am I going to find, where are you going to find, especially the roller coaster folks, the final position, the final temperature at the end of the simulation? How would I get the end temperature at the end of the simulation?
The y variable end.
Y variable end, exactly. Let's go back to our picture. What do we have in our output? We have a bunch of t's, and the number might change, right? If I'm specifying the number of intervals, and there's always one more time value than those. But the key thing is the last one. The last one is the one that goes with the end of my simulation. So y end would be the perfect choice for that. So our sim end is y end. We don't have to specify it. Or if you want to be more specific, it would be y at n plus 1. That's another way you could do exactly the same thing. And the analytic end, let's write it out because it sounds dirty otherwise. Analytic end is equal to 25 times the exponential of minus k times t end minus 5. Error. And then we do a print statement. And let's go with 4D. All right, so this is all stuff we've seen before. Get a nice print statement just to have things line up nicely. I'm going to try that 4D thing. And we'll give 8 decimal digits after the 8 digits after the decimal. And we'll see how that runs. Lovely. OK, so we get some error. It's pretty small, but it's there. What we can do is then rerun that a bunch of different times with different n values. Where did my n get set here? There it is. So we can run this again with 200. We can run it again with 400. And we'll run it again with 800. All right. Hey, when I double the work that I'm doing, i.e. use twice as many intervals and have twice as long to go through the loops, what happens to the error at each time? Halves. Hey, where have we seen this before? One of those things like 2 weeks ago with the integration. Numerical, hey, what are we going from? From a derivative to an original function? It's kind of like integrating. And so you'll see, as we go through this week, a lot of resemblances between left-hand rule, trapezoid rule, Simpson's rule, Euler's method, and the next methods that are coming up. We'll see tons of parallels, and this is our first inkling of that relationship. And actually, if you take a step back and just ask yourself, hey, formula-wise, what's going on here? What was the left-hand rule? It said add things up, add up heights times widths, f times delta x, f of x times delta x. We're doing exactly the same thing here. It's a little more confusing because there's 2 values that might play a role, t and y, instead of just an x. But if you look back at left-hand rule, it's f of x times delta x. And we're doing f of t times delta t here with just an extra y. So there's lots of resemblances, and the performance aligns with that. Every time we double the work, we have the error. But it also points to maybe there's ways to improve this, so we're going to do that next.